Hi, everyone. It's a great pleasure to be here. My name is Melissa Shahbandeh. I'm a postdoc at the Space Telescope Institute. And today I'm going to talk about how we're using Keck plus JWST to understand the origins of cosmic dust. So why do we care about cosmic dust? Because dust is behind star formation, planetary science. If we can understand how dust absorbs and scatters light, then we can understand the color of background objects better. We can also understand the temperature, the heating, cooling rate, and density of the ejecta or the area where the dust is forming. We can also get information about the latest stages of massive star evolution. So why do we care about supernovae? Because initially it was thought that AGB stars are behind a significant amount of dust that were found in high redshift galaxies, but AGB stars weren't old enough at the time to produce that significant amount of dust. So what's the alternative scenario? It's supernovae because they can efficiently and quickly spread a lot of material throughout the space. So why are we using Keck and JWST? Because to study dust, we need to go to the near-infrared and mid-infrared because near-infrared and mid-infrared is transparent to dust. There's very limited sample, and it has not been studied well. There's the wavelength coverage and sensitivity to warm and colder dust that Keck and JWST can provide us that can help us understand the ultimate goal, which is understanding cosmic dust in the early universe. We're using Keck in tandem with JWST to get data of all these supernovae so we can ultimately understand the role of dust in the early universe. And what JWST does is that it helps us observe later epochs of supernovae that was not available before with Spitzer. So we have a lot of programs on Keck and JWST with mainly the focus is that we're trying to study dust. So we have a lot of programs on Keck, such as KITS. Alex Filipenko has provided us with a lot of spectra. We have a lot of JWST programs that are focusing on dust that I've mentioned here. I'm not going to get into that, but if you have questions or you're curious about that, let me know. So what are the goals? Let's say we have the data. What are the goals that we're trying to achieve? We're trying to understand if the dust is newly formed or is pre-existing in the ejecta of supernovae. We're also trying to understand the heating mechanism of dust, and we're also trying to calculate the amount of dust and get a better understanding of how dust evolves over time. So Keck, optical, and near-infrared NIRIS and LRIS can help us distinguish between newly formed and pre-existing. Keck optical spectra can help us understand if the heating mechanism is by optical, UV, or IR. And JWST data can help us understand how much dust is there and help us have a better understanding of the dust evolution. So this plot has too much, just bear with me for a little bit. So I've divided how we look at dust evolution in supernovae into 3 different phases. So phase 1 is when we look at dust precursors. These are the molecules that can cool the ejecta of supernovae to temperatures at which dust can form, such as carbon monoxide and silicon oxide. And then we have phase 2, where these precursors are evolving. And then we have phase 3, which is where these precursors have smeared out. We don't see them anymore, but then we expect to see signatures of dust in the spectra or in photometry. So we have a lot of JWST programs that have a corresponding Keck optical or near-infrared programs that we're trying to obtain data of several different types of supernovae from type 2P to 2N to strip envelope to have a better understanding of how dust is forming in these supernovae. So we lack data in the early times around explosion and a couple, like about 30 to 50 days after explosion. And we also lack data in the late times. So a lot of our programs that we have right now in cycle 1, cycle 2 of JWST are focused on the early time, and we have several that are focusing on late time. And we are also getting optical and near-infrared spectra with LRIS and NIRIS of these supernovae to create a SED going from the optical to all the way to 25 micron to investigate the dust evolution. So here I'm showing you this diagram shows that when the supernova explodes, depending on the type of supernova, we expect to see dust precursors, CO and SIO, showing up around 70 to 100 days. and then we can expect them to evolve up to about 200 days, and then after 300 days, we expect them to disappear, and then we expect to see dust signatures showing up. So one of these targets is a type 1C 23 dBc that exploded this year in March. So we triggered JWC observations on this and Keck LRES plus NIRES. So we have about more than 10 LRES plus NIRES spectra of this supernova. We studied the CO molecule from early time in March to about a month ago. We have JWST near spec and MIRI mid-infrared spectra of this supernova. And initially, it wasn't believed that strip envelope supernovae can contribute to the significant amount of dust observed in the early universe, but the goal of this program was to test that idea. So what we found is that, so on the left here, you can see this spectrum obtained by Brian Foley, Gao, and Kitt's group that shows the CO profile showing up around 2.3 micron. This is the first overtone of CO. So we expect to see the fundamental band of CO showing up around 4 micron. So why we need Keck plus JWC is to have the first overtone in 2.3 micron, and then have the fundamental around 4.5 using JWST, and then have mid-infrared spectrum to look at SIO signatures. So here we can see, I'm showing you one of the spectra. We have about 10. So here you can see these vibrations that show the vibrations of the CO molecules, and then we have models to model this profile over time and get a sense of how CO evolves over time and how the temperature goes from about 6,000 to about 1,000, which can tell us more about the environment of where the dust is going to form. These are the JWC spectra of the supernova. So up there is from 1.7 to about 5.2 near spec JWST. So here we can see the fundamental. So this one was the first overtone. And then, so this one is the fundamental band, and we can, the reason we need Keck and JWST is because of this CO molecule that we want to have both the first overtone and the fundamental band to model them better and have a better understanding of the temperature and the velocity. And we also have the mid-infrared spectrum. What you see here that I've marked is the SIO molecule showing up, which nobody actually expected, but it's significant result, having all this spectra going from optical to mid-infrared. We have, and that is why Keck is crucial, because in December or January of next year, 23 dBc is going to be fainter than 20 mag in K. So the only ground-based telescope that can observe it is Keck. So it's very critical that once we're going to get the second and third epoch with JWST, we also have the Keck spectra to look at the first overtone of CO. Otherwise, we cannot really understand the evolution. We have another supernova that looks at the early dust precursors. So this time we have supernova type 2P, 22ACKO. This is a nearby type 2P supernova. So again, we have NIRES spectrum. We don't see CO or SIO in this one because this is a type 2P that has hydrogen layers intact. So it takes longer to see the CO molecule showing up in this supernova. We expect to see the molecules after about 100 days, but the previous one, we saw the CO and SIO showing up in both NIRES and JWST at around 50 days. This is the JWST data of this same supernova. So NIRES and JWST helped us to have a full SED, the first core cup supernova that has a full SED from 4,000 angstrom to 250,000 angstrom. We also used, so bottom left here, you can see the Keck spectrum, and this one is a near spec JWST spectrum. We use both of these to get an upper limit for the CO mass, which we do not expect to see, so we got an upper limit. So in the later epochs, we can have a better understanding of where we started and how much CO and dust has been formed over time. Going back to the same diagram, so now I'm going to focus on phase 3. So we have some programs that focus on phase 3. So one of them is a cycle 1 program. Ori Fox is the PI of that at Space Telescope. So for this program, we had 5 type 2P supernovae that still have their hydrogen, And we either saw some signatures of dust with Spitzer, or we used Keck spectra to see the CO molecules in the past. So we use these supernovae that are older than 5 years right now to see how much dust we can measure, or of the composition of dust. So 2 of them are published right now, 2017 EAW and 2004 ET. So here on the left, you can see the Spitzer image. On the right is JWST for 04 ET. This one is 17 EAW. On the left, Spitzer. On the right is 17 EAW. You can see how brighter 04 ET is. First is because it's older and it has much more dust that we can, after about 20 years, we still can see it pretty bright in JWST data. So how can Keck help us to answer some of these questions that we had? So one thing is that we need to understand if dust is newly formed or is pre-existing. So LRES, optical spectra, can help us look at the H-alpha lines. And if we see a blue shift in the H-alpha line, that means there was newly formed dust in the ejecta that created this blue shift, and therefore it's an indicator of a newly formed dust. And then we also, if we model JWC data, then we can understand if the dust radius is below the shock radius. And if that's the case, then that also is another indicator that dust is newly formed. So we used LRES spectra of both of these supernovae, and both of them showed a blue shift and told us that this dust is probably newly formed in the supernovae. And we used JWC data to have a better understanding of how much dust is there and the composition of dust. So LRES helped us distinguish between newly formed and pre-existing. LRES also helped us to exclude the optical as a heating mechanism, and JWC helped us to have a better understanding of lower limit on the dust mass. We have another program. We're looking at the interacting or type 2N supernovae. It's similar to the other one, but this time we have different type of supernovae. So we have a spectra of these supernovae both in optical. We have data from past in the Spitzer data. So here I'm showing you the Keck LRES spectrum obtained 18 years later for this supernova by Alex Filipenko and Berkeley team. We have a NIRS night coming up in about a couple of weeks, so we're going to get a near-infrared spectrum here, and then we have mid-infrared. So we're going to have all the way from optical to 25 micron, which can help us model this dust from all the way from optical to near-infrared to mid-infrared, and get a better understanding of the temperature, the dust mass, the dust composition, if these features that we see here are real, and have a better understanding of how these interacting supernovae are producing dust, and if they are major contributors to dust formation in the early universe. And why do we need more than one supernova? With Keck, hopefully we get more time, and with JWST, because if you look at this diagram, I'm showing you the dust mass versus phase. So these data points here are all these supernovae that had some sort of dust mass measurement with either Spitzer or other instruments in the past. And this one over here is 1987A, which was the closest supernova exploded in our lifetime. So there's a gap here after about 2,000 days to 10,000 days. And this is where we're trying to observe more supernovae to fill out this gap so we can have a better understanding of how dust evolves over time. And here's my summary. Thank you so much for listening.